Is a 4 always just a 4? In this second lesson of our Numbers Foundation course, we explore place value and why we call it the power of position. We will break down the number 4,444 to show how one digit can represent thousands, hundreds, and tens. If you're mastering basic maths concepts, this breakdown of our number system is essential. In the number below, 4,444, the first 4 standing tall in the thousands place isn't just a 4, it has a value of 4,000. The second 4 in the hundreds place drops in value to 400. Moving right, the third 4 is in the tens place, giving it a value of 40. And finally, the last 4 in the ones place is simply 4. When we add these individual place values together, we get the total value of 4,444. This is the essence of our number system. The digit tells you the what, but the position tells you how much. In our last lesson, we looked at types of numbers, but how do we actually build them? It all comes down to place value. With just 10 symbols, 0 to 9, we can write any number in existence because their position tells us exactly what they are worth. There's one simple rule that governs everything in this base 10 system. Each place is 10 times bigger than the one to its right. As you move left, you aren't just shifting a digit, you're increasing its power by 10. Look at this scale. From the ones to the tens to the hundreds, and all the way up to the millions. Every jump left is a multiplication of 10. Conversely, every step to the right is a division by 10. We use power of 10 to track this growth. It's the engine that runs our entire math system. Let's put this into perspective with something we all use, money. Think about the digit 5. In the ones place, it's just 5 1-pound coins, that's 5 pounds. Move it one spot left to the tens place, it becomes 5 10-pound notes, that's 50 pounds. One more jump to the hundreds place, and those same 5 digits represent 500 pounds. The digit 5 never changed, but its position changed its entire value. That is the power of position. Now that we understand the theory, let's look at a practical example. The number 4,372. To find its true value, we look at the position of each digit. The 4 is in the thousands place, the 3 is in the hundreds place, the 7 is in the tens, and the 2 is in the ones. When we organize this into a place value table, you can see how each digit carries its own weight. This is called expanded form. It is the DNA of the number. But what happens when we multiply this entire number by 10? Remember what we just said. Multiplying by 10 makes a number 10 times larger, shifting every single digit one place to the left. Watch the transformation. As we multiply by 10, the 4 jumps from the thousands to the 10,000s. The 3 moves to the thousands, the 7 to the hundreds, and the 2 to the tens. Because we've moved everything left, we have an empty ones column, which we will fill with a 0. Our new value is 43,720. One simple shift, 10 times the power. We've mastered making numbers larger. Now let's look at the reverse, dividing whole numbers by 10. This is where we see the true symmetry of our number system. Take the number 4,370. It's made of 4 thousands, 3 hundreds, 7 tens, and 0 ones. But what happens when we divide this entire value by 10? Here is the golden rule to remember. Dividing by 10 makes a number 10 times smaller, shifting every single digit one place to the right. Now watch the shift. The number 4 moves from thousands to hundreds, the 3 to the tens, and the 7 to the ones. Our result is 437. When a whole number ends in a 0, dividing by 10 is as simple as shifting that 0 out of the picture, leaving just 437. But what if there isn't a 0? Let's look at 4,372. We have 4 thousands, 3 hundreds, 7 tens, and 2 ones. The 4, 3, and 7 moves into their new homes, from thousands to 100 for 4, hundreds to tens for 3, and tens to ones for 7. But look at that too. It has shifted past the ones place into a brand new territory, the tenths. Think of it this way. Because we are dividing by 10, every digit becomes 10 times smaller. That means the 2 doesn't disappear, it shrinks. It was worth 2 ones before, but when we divide it by 10, we're also dividing that 2 by 10. So it's not 2 whole ones anymore, it's now 2 small pieces. Each piece is 1/10. 2 of those pieces makes 2/10, and we write that as 0.2. The digit 2 stays the same. Its value changes because it has moved from the ones column into a smaller home on the right, the tenths place. Same digit 2, just in a smaller place and smaller value. The final answer becomes 437.2. This proves that place value doesn't just stop at 1, it continues moving right, getting 10 times smaller with every single step. And by shifting that 2 past the ones place, you've just unlocked the entire world of decimal numbers. Now that we have unlocked the doors to decimals, let's step inside. Decimal place value isn't something new. is simply an extension of everything we already know about whole numbers. It allows us to represent values smaller than 1. The decimal point has one powerful job. It acts as a border patrol, separating the whole numbers on the left from the decimal part on the right. Think of it as the anchor of our entire number system. Everything to the left of the decimal point is a whole number. Ones, tens, hundreds. Everything to the right is smaller than 1. Tenths, hundredths, thousands. The golden rule still applies. Dividing by 10 makes numbers 10 times smaller, shifting digits one place to the right. But here is the most important thing to remember. The decimal point is a fixed separator. It never moves. Only the digits shifts around it. That's why when we divided 4,372 by 10, the 2 didn't disappear. It crossed the decimal point and became 0.2. Now notice something powerful. Whole numbers usually end in S. Tens, hundreds, thousands. Decimal place ends with THS. Tenths, hundredths, thousands. That THS is your signal that you're dealing with a fraction of a whole. Now look at the mirror effect in our table. The ones place sit at the center. To its left is tens. To its right is tenths. To the left again is hundreds. To the right again is hundredths. It's a perfect reflection that continues forever. And once you understand this symmetry, you understand decimals. This is the foundation of every decimal calculation you will ever do. Now that we know the decimal point is a fixed anchor, let's see what happens to the digits during the calculation. Let's start with the example 1.5 divided by 10. To divide by 10, we follow the same logic as before. The number gets 10 times smaller, so every digit shifts one place to the right. We have 1 in the ones place and 5 in the tenths place. When we divide by 10, the number becomes 10 times smaller. In terms of place value, that means every digit shifts one place to the right. The 1 moves from ones to tenths, and the 5 moves from tenths to hundredths. So 1.5 divided by 10 becomes 0.15. Before we move on, let's look at 2 crucial rules. 1. The decimal point stays still. It never moves. The digits are the only things jumping over it. In number 2, we see something very important. We needed a 0 in the ones place. That 0 is a placeholder. It doesn't change the value of the number. It simply holds the space so the place value system stays organized and balanced. Without that 0, the digits would slide incorrectly and the structure of the decimal place value chart would break. Simply put, the 0 tells us there are no whole numbers left. The numbers are now entirely in the decimal part. Now for the reverse. Let's analyze 1.5 times 10. Multiplying by 10 makes the number 10 times bigger, shifting every digit one place to the left. The 1 moves from ones to tens. The 5 moves from tenths to ones. This gives us 15.00, which is simply 15. Notice again, the decimal point did not move. The digits moved around it. Our final answer is 15.00 or simply 15. By just moving these digits across the decimal point, we've completely changed the scale and size of our number. Dividing decimals by 10 shrinks the value. Multiplying decimals by 10 expands the value. Right shifts are smaller, but left shifts are bigger. Same digits, same decimal point, different place values, different scale and size. Now let's log this in with some worked examples. First up, what is 0.07 times 10? Remember our rule. Multiplying by 10 makes the numbers 10 times larger. Because we are multiplying by 10, the digits must move one place to the left. This means the 7 shifts out of the hundredths into the tenths place. Notice that I say THS at the end. Our final result is 0.7. Notice also how the decimal point stayed exactly where it was. Now let's try a division problem. What is 47 divided by 10? When we divide by 10, the number becomes 10 times smaller, so we need to shift our digits in the opposite direction. Shift every digit one place to the right. The 2 moves from the ones into the tenths place, and the 4 moves from the tenths into the ones. Following the shift, we place our decimal points between the 4 and the 2. The final result is 4.2. By focusing on digit movements instead of moving the decimal point, you understand what's really happening in place value. Multiplying decimals by 10 move digits left. Dividing decimals by 10 move digits right. This is the mental maths shortcut. And once you see that pattern, you can handle any decimal movements instantly when dividing or multiplying by numbers like 10, 100, or 1000. You're not memorizing tricks, you're understanding the structure. Now it's time to put your skills to test with some practice questions. I want you to pause the video right now, grab a pen and paper, and try to solve these using the digit movement method we just learned. Let's look at what we have. In question 1, remember, multiplying by 10 makes the number larger, so move those digits to the left. In question 2, dividing by 10 means movements to the right. In question 3, even with a whole number, that 6 is going to jump past the decimal point. In question 4, keep that decimal point fixed and move your digits. And finally, for those of you who want to master mental maths, here is your challenge in question 5. Question 5 requires you to work backwards. If you divide to get there, What do you do to get back? Drop your answers for the challenge in the comment section. I will be responding to your answers. Don't forget to subscribe and hit the notification bell so you don't miss out on our next lesson.